speaker is Professor Yimin Bie from Jilin University. Probably you will have 10 to 15 minutes time, and then we can proceed to the two more presentations by scholars from Beijing Institute of Technology.
Okay, thank you. Can you see my screen?
Yes, I can.
Okay, hello everyone. Thank you for attending this meeting. My name is Yimin Bie from Jilin University, and now I have about 10 minutes for my report. The title is Optimal Daily Air Conditioner Usage of an Electrical Bus. I have 4 parts in my report. The first part is introduction. Electrical bus has the advantages of low noise, high driving stability, and zero emission. It's of great significance to reduce the emissions of urban vehicle pollutions. At present, the number of electric buses put into operation in China accounts for more than 90% of the world. However, due to the impact of onboard battery technology, electric buses still have short driving ranges. Moreover, subject to the land use problem, no charging facility is equipped at the original and the terminal stops for buses. Therefore, the buses have to get recharged at the depots when they finish the daily operation. Moreover, the non-linear energy consumption exists. For example, with the decrease in SOC and the energy consumption will increase rapidly. In such condition, bus drivers generally have different degrees of anxiety. They worry that the frequent use of the AC will accelerate the energy consumption and then lead to the service interruption because of the run out of electricity. Even if they know there will be a high SOC left at the end of the last trip, according to experiences, they did not turn on the AC during the operation, or only turn on the AC in the last few trips. The anxiety pays greatly negative impacts on the travel comfortable of passengers. For example, these data were collected from Mexico City. In this column, it denotes the SOC at any time of one day. We can see that the left SOC is about 50%, and the energy consumption of that day is about 95. This is the data for another bus route 103, and these data were collected about 10 days ago. This is the temperature. The temperature is about -10 centigrades, but the AC usage is the bus drivers didn't open the air conditioner. Therefore, it's necessary to consider the number of trips served by an electrical bus during the operating hour, the temperature and the travel time of each trip, and establish an optimization model for the AC usage. The second part is the model development, and we use N to denote the number of trips that a bus needs to operate. The trip time of trip N is Hn minutes, and it includes 2 phases. Phase 1 is the electric bus operates from the starting station to the terminal station. Phase 2 is the electric bus waits for passengers in the terminal station. So the waiting time is Hn minus Tn. And the operation from the depot to the original station is defined as trip 0, since it needs to consume a certain amount of electricity. Setting integer variable xn expressed different gears of the AC, and the power of the AC with gear xnu is denoted by PAC. In our study, we need to maximize the value of objective function and establish the following chance constraint programming model. Alpha and beta are predetermined confidence levels. F is the objective function and represents the total time for passengers to enjoy comfortable temperature on our trips. Maximum F will be the maximum value that the objective function achieves with at least possibility alpha. Lambda is a critical threshold which can ensure that the electrical bus has enough battery energy to return to the depot after the end of the last trip. In equation 3, P and V is an index to denote the comfortable level. When it's larger than -1 and smaller than 1, the passenger will feel very comfortable. And in this page, we need to calculate the cabin temperature. Cabin temperature is the most important part of this study. The cabin temperature will affect the comfortable level of passengers, and it's affected by five factors. For example, the number of passengers in the bus, and the ambient temperatures, the area of the glasses, for example. The equation for cabin temperature is very complex, so they are not displayed here. WNU denotes the waiting factor, and the passenger's willingness to turn on the AC is affect the waiting factor. It's directly proportional to the deviation of the ambient temperature from the comfortable temperature. As the ambient temperature changes slowly, the average ambient temperature of triple N is used to calculate the weight Wn. Here we can see that PPD can be calculated based on P and V, and PPD is also used to calculate the weighting factor. The energy consumption model is fitted based on the field data in Mexico City, China. It's mainly affected by trip times and temperature and the initial SOC and the AC usage. The objective function and constraints of the model involves travel time Tn, which is a random variable affected by uncertain factors such as the road traffic state, signal timing plans at intersections, and passenger demand at stops. The traditional way to solve the chance constraint programming model is to transform it into its equivalent form. However, for this problem, it's hard for the transform. Therefore, we use the random simulation and the genetic algorithm to solve the proposed model. Random simulation samples random variables based on probability distributions. In this paper, random simulation is used to calculate the probability measures. And the genetic algorithm is a method to find the optimal solution by simulating the natural evaluation progress, and is used to get the solution. Section 3 is case study. In this section, the electrical bus route 108 in Mexico City, Jilin Province, China, is taken as an example to validate the proposed method. And the length of this bus route is 17 kilometers with 30 bus stops. For electric bus, it operates 10 trips one day. And here we display 11 trips, and trip 0 denotes it departs from the depot to the original station of trip 1. And here is the scaling table of the bus we choose. And the electrical bus, we made data analysis and use KS test to find that the travel time Tn follow truncated normal distribution with different parameters. Here is the probability density function. And there are seven gears of the AC, and here is the power of each gear. These two figures displays the temperature and PPT curves with given conditions. From the red line displays as the ambient temperature curve, and the green line is ambient temperature curve. The purple line is the PPD curve. These curves are all get and known conditions, and the predicted cabin temperature are close to true values. The second part is the energy consumption and estimation equation. In this part, the unknown parameters are fitted, and the MSE is 0.152. And here is the optimal result. We can find that in this group, there are 21 data. However, we have 11 trips, because for trips 1 to trips 10, there are two phases for each trip. So there are two decision variables for each trip, from trip 1 to trip 10. Here alpha is 0.9 and beta is 0.95. And the last part is some conclusions. The stochastic travel time should be considered during the operation, because it will influence the energy consumption during the operation, and the estimation results for energy consumption will affect the usage of AC. And the proposed optimization method is able to produce optimal AC usage, considering the comfortable level of passengers, which is useful to improve the bus service level. The most important part of this study is to calculate the cabin temperature with the impacts of number of passengers, AC power, the ambient temperature, and the bus body structure. That's all. Thank you very much.
Thank you, Professor